tell us about hidden subgroup problems?
Alright, good. So, well, good morning and welcome to anybody who's traveled here, like me, I guess. I will be talking about diagrammatic treatment of the hidden subgroup problem, or better, diagrammatic formulation of the standard algorithm to solve the hidden subgroup problem in the abelian case. So first, perhaps I should say a couple of words for those who are not already familiar with what the problem is about and why it's important. So the hidden subgroup problem gives you some map from a group into a set, and it makes a promise on this map. It says that there is some normal subgroup. This group is abelian in the case that we will treat. And it says that there is some subgroup H, which is not known, over which the map is constant. So it says that this map over the cosets, which the map is constant. So it says that this map factors through the quotient group. And furthermore, it says that on different cosets, it takes different values. So it factors like this as the group quotient map and some map of sets, sending each coset of the group, the subgroup H, into a different value of this set. So we're given this map, and the task is to find what H is.
I've already got a stupid question.
Yes?
Thank you, Stefano. F and S are maps in the category of sets.
So this is set. This is set. Well, this is technically set, but it's actually
It's a group.
Yeah, it's in algebra.
So it's a group map.
It is a yeah, the quotient map is a group map. It's the standard.
Thank you.
Yes. So this is not immediately given as a black box F, although most formulators of the hidden subgroup problem say so, because you have a classical map, and technically you have to construct a unitary oracle from it. So what the problem really says is you're given a circuit that computes F given some unknown parameter, you don't know how to simplify it, and from this circuit you can construct some unitary oracle, or you can just avoid the problem altogether and say that you're given a unitary oracle already, which encodes F in some orthonormal basis of some appropriate Hilbert space. Let's put a sand down the orthonormal basis like this, and another orthonormal basis here like this. So technically, most formulations just take this as a given oracle that encodes the map coherently. This is in F and K. Okay? So although the problem is formulated like that in terms of classical maps, technically what you really need is a quantum oracle, so let's start with a quantum oracle. The interesting part of all of this is that the hidden subgroup problem encompasses some of the interesting problems that quantum computers seem to be better at solving than classical computers. For example, Shor's algorithm is a special case of the hidden subgroup problem, and the discrete logarithm is a special case of the hidden subgroup problem. But these don't really say much about the separation between quantum and classical. What's interesting is a different problem which is not really practical at all. It's called Simon's problem, and it is possible to show that relative to the oracle that you're given, Simon's problem separates BPP and BQP. So relative to an oracle, Simon's problem provides a separation between what probabilistic computers can do and what quantum computers can do. So this is why this is an interesting problem by itself in the abelian case. In the non-abelian case, if it was possible to solve it, it's not known whether there is an efficient way of solving the non-abelian version with a quantum machine. It would also solve the shorter vector problem, which is NP hard. So it would in particular show that NP is a subclass of PP at least. And it would solve the graph isomorphism problem, which is not as good as the subgraph isomorphism problem, which is incomplete, but it's still an interesting problem that's not known to be solvable in quantum time. So yes, it's a large family of things that can be done by just looking at group structure. And the basic idea of all of this is that you perform Fourier transform, and the Fourier transform finds the pattern associated with the subgroup, and from that pattern you can reconstruct something. So, since the unitary oracle seems to be a fairly key part of all of this setup, let's look at what a unitary oracle is. It's possible to show that an appropriate unitary oracle that encodes that map F can be written like this. And I'll go over the notation in a second. Without loss of generality, I will choose X to be strings of bits of length n for some fixed level. The reason I do this is because this comes with a group structure, an abelian group structure in fact. It's the abelian group of pointwise XOR. And that will be useful in constructing the unitary in a second. So for now, we will have a unitary with two, well, it has to have somewhere the original group, and somewhere it also has to have the set that F takes values into, but it also has to be a unitary. So the easiest way to construct one such unitary is not unique in any way, but it's a standard one, is to just put both domain and codomain at the beginning and at the end, and rely on ancilla. And usually this is represented like this. This is represented like this. And then you can take the adjoints of these. And it turns out that very much. This co-multiplication, a co-unit, a multiplication in a unit has an algebra structure. It's an algebra and algebra structures which interact. It's called a Frobenius algebra. In fact, because this is an isometry, this is a special Diagrammatic algebra, and this is clearly commutative, so it's a special commutative Diagrammatic algebra, which is just a long word for something which is really useful. And one could ask what those algebras have to do with anything, and it turns out that they characterize orthonormal basis exactly. So any Dagger special commutative Frobenius algebra, it's just long, so I'll write that, corresponds to an orthonormal basis. This is just an isometry from the group algebra to the group algebra times itself, times with itself. And this, the adjoint of this is going to be sort of an isometry, in fact, but it's a multiplication, and I'll get in a second to what that is. This is a special Frobenius algebra, which means that this happens. This is the same as asking that it's an isometry, but you can relax that requirement and you can consider more general Dagger commutative Frobenius algebras, which don't have this, but instead have, for example, this requirement for some positive natural. Now, this doesn't give you orthonormal basis anymore. So something in this form where the multiplication is not an isometry, but it's an isometry up to some positive scalar factor. And I will write a double commutative Frobenius algebra. In fact, this is quasi special, but it doesn't really matter. That gives rise to an orthogonal basis, not an orthonormal. So the only thing that changes is that there is no normalization of the basis elements anymore. They are still orthogonal, but you may have to normalize them by hand. Now this, I will use a convention, and I will say that each group algebra comes with a pair of these structures. It comes with a chosen orthonormal basis, the basis of the group elements. And I will denote that by this Frobenius algebra. I will just write it white, and I will, yes?
Can I show my ignorance? How is the group algebra defined?
A group algebra.
Yeah, the group algebra.
So a group algebra, this is just a Hilbert space. This is just L2 of G. but it comes with a linear extension of the group multiplication and the group unit encoded as an element. So this determines the basis of group elements. And then one of these elements will be marked, and there will be a linear extension of the group multiplication, which I will write like this. So this is the map that takes G and H and sends them to G plus H in the group. And this is just the zero, the unit of the group. In order to not write too many colors, because it's a bit cumbersome after a while, I will just write the name of the group next to them, so that it's clear which one I'm talking about. And I can simplify notation a bit, and I can say that this is the group operation of Z to the n, because it's XOR, and this is just the basis algebra of group G. Now it is possible to show that this is a unitary, and the proof relies on the following fact. It relies on the fact that these two bases are not just unrelated in general, they have a very strong property. They're called strongly complementary. They satisfy a certain set of equations, by algebra equations and coherence equations, which I'll just write very quickly. One of them says that multiplying two elements in the group and then copying just copies the elements, and that's due to the fact that that's truly a well-defined group multiplication. One of them says that the unit of the group is in particular an element of the basis. Well, that was sort of obvious. And the other one says something slightly more interesting, which I'll get to later on. Now these three define strong complementarity. They're called the unscaled by algebra and coherence equations. They, in fact, define what the relationship between these two algebras, because there's a theorem by Alex in his thesis that states that, in fact, pairs of strongly complementary structures, algebras, are completely classified by finite Abelian groups. So not only every group algebra has a pair of such things satisfying these equations, but in fact, given any orthonormal basis and any finite Abelian group, there is one such operation with these properties. So that's an exact characterization of finite Abelian groups, or better, linear extensions of finite Abelian groups. So finite Abelian group algebras are just these things. What is interesting later on, I guess, is that they also satisfy, as a consequence, the Hopf law. Now the Hopf law might just be a handy diagrammatic thing, but in fact it says that elements of this basis and elements of another basis that we'll talk about in 5 minutes are unbiased. And this is sort of interesting because it gives you an uncertainty principle in a very, very strict sense. Good. Now knowing that this algebra and the algebra defining the basis that f takes values in, so let's remember that f was a classical map, it was valued in z2 to the n, so strings of n bits, and therefore it sends elements of these orthonormal bases to elements of the orthonormal basis associated with the white structure, let's call it, for n-bit strings. Using the fact that these are strongly complementary, it is possible to prove that this thing is actually a unitary, always. So it's a good candidate for a unitary orthogonal. I will not prove this here. It's in a paper by J.B. Vickery and Zen, as I said, in 2015. But that's the starting point of the hidden subgroup problem algorithm, diagrammatically at least. Is everybody with me up until this point? Are there any questions? Then I'll move to more interesting one. How do we use that and construct a protocol which solves the hidden subgroup problem? Well, first of all, we have to apply it to something, and then we have to measure it somewhere, and that's really all that there is. Contrary to Shor's algorithm, there is no pre-processing and no post-processing. Well, just a little bit, but nothing that is worth writing diagrammatically. So what are our chosen initial states for this unitary? In here we will place the unit of Z to n as a group. So the bit string long n with all zeros. And here we will place the unit of this special commutative for this algebra, which is not normalized, so we have to normalize it. And the normalizing factor is just 1/g. Nothing special. Now this is a unitary, this is initial state, this is a pure state altogether, and it's by Cartlet state, and we will make local measurements, and we have to choose our measurement basis carefully. The first one is relatively straightforward. We measure in the basis of the bit strings. Because ultimately, we know that the function f was a function from g into bit strings, so we're interested to know which bit string came out. The other measurement is more interesting, because it's not in what we know to be immediately associated to an orthonormal basis. So this we know is associated to the orthonormal basis of n bit strings. And this we know that we have an algebra, but we don't really know what the basis looks like if there is a basis. Now, we know there is an orthogonal basis, because this multiplication and the unit, we can take the joints, and the joints together with the original maps form certainly a better commutative from this algebra. You can prove this. That's nice. It is associated to some orthogonal basis, and that basis turns out to be really interesting. It's the basis of multiplicative characters of the group. So this one is associated to the basis given by the chi's, such that chi from G to S1 in GRP is a multiplicative character, where I define the linear state associated in what is, I hope, the obvious way. It's just the obvious linear extension. I mean, this is a linear map, so one can just turn it into a state. Okay? This is an orthogonal basis. It's not a, yes, this should have a little bit. It's not an orthonormal basis, but we'll take care of normalization later on by hand, as we did with the unit of the algebra. Now, because we're measuring in this basis, but we prepared in the group basis, what we're doing is effectively a Fourier transform. Now, it's hidden in the fact that the measurement is done in different bases, but you could have equivalently written this as, I don't like it, but we can, as measuring in the original basis given a Hadamard transform first. Those are the same. Because the Hadamard transform just maps elements of one basis to elements of the other basis, and up to some rearrangement of the labels, you can always do that. However, this requires a lot more work diagrammatically, and this is a lot more natural, and it tells you immediately that you're doing a Fourier transform. So I'm going to stick with this one. Good. Now, we have this. What we want to prove is that conditional to having observed some bit string here, any bit string, it doesn't really matter which. What we will observe here is not a general character, it's a very specific character that will allow us, to reconstruct what h was upon enough sampling. So we want to know that whatever we can observe here will not be a generic character, but will be sampled from some appropriate subgroup of the group of characters. So that's what the algorithm is really all about. I'll clear this if it's okay. First of all, we can simplify that a little bit. So I said that this is in particular a pure state. I'm showing a different color. Yeah. This is in particular a pure state. So it's the first step to figure out what that state looks like. Well, because we've done things diagrammatically, it's actually quite straightforward. You don't have to do any sums or any counts. You obtain that this, which is what I wrote. I'll omit the labels in case until it's necessary to put them back. This state is actually simply this. It's Bell state where I apply f to one of the two events. Now, this f is not a random f, it's an f with a promise, and I can rewrite it to be, so this is in the group algebra of G, then there will be a quotient map, then there will be something in the group algebra of G over H, then there's going to be an isometry, which I write as S, and then I'm going to get something in the group algebra of bit strings. Okay? And I can just turn this around because it's a quotient map, so in particular I can write it's a joint on one side, an S on the other side, and I can use a Bell state in a different space. I can use the Bell state in the group algebra of the quotient group. I just rewrote this. I didn't really do anything. Now assume that you have observed some bit string B from this measurement. Not all bit strings will be observable, unless, well, I guess in general it is possible that not all of them will be observable, but suppose that you will observe one. So the state you have collapses into a mixed, there is a one over G, I guess. Collapses into another state, which can be written as follows. Now I've said, suppose I've observed some string B, so I'm just going to put the string B here. And because I'm doing conditional probability, I'm going to have to renormalize, taking away the probability of that string. Now I know that every coset is mapped to a different element, and this function is balanced, so the probability of that will just be the probability of one coset in G modulo of H, and it will just be H over G. So I just divide by that, and I get E over H, but I'm writing these as amplitudes rather than probabilities for, I don't know, because it's easier to read. And that's what I should normalize by. So I take the amplitude that would square off to the probability that I'm taking away with the condition. Now this state I can work with, because I know that, well, this particular outcome B, this bit string B that I have, corresponds to some unique coset. Now, the group algebra, this is also group algebra. In particular, it also has an orthonormal basis, which I will write like this. Where I'm going to take one representative per coset, just for diagrammatic sake. It doesn't really matter which, and it doesn't come into the calculation zone. Now this was an isometry, so necessarily I can reduce this particular state to GB plus H for the appropriate GB, with, I'm just going to simplify the root of size of G for my own use, and because it's useful really diagrammatically. Now this is not an isometry, because it's the adjoint of a quotient map, but it's not even normalized. With this factor, it's normalized. So it will send things of node 1 to things of node 1. So this, I write it in next Q because it belongs there. And this is a normalized state. So So my state right now is just Q normalized applied to an appropriate quotient state.
So that's the adjoint of the quotient.
That's the adjoint of the quotient map, yes. So I don't know if it helps you. I can write the dagger explicitly, maybe. Traditionally, I let the shape say which one is which, but I guess that's it. We have this state. As of now, we've done no sums. We've done no simplification whatsoever. So as long as we can prove that this state measured in that basis gives what we want without relying on sums or group theory, then this was truly a full diagrammatic proof. And that requires a little bit of extra work. And that's the final part, I guess, and the interesting bit. So I will have this measurement applied to that state. And I want to say what is the probability of observing some specific chi. Okay? So the probability of observing some specific chi can be given by just post-selecting chi without renormalizing. Because renormalization was needed to just take away that probability. So if I don't renormalize, this number will just be the square root of that probability. So I'm interested in this. This will be an amplitude, and what I want to show is that the squared of that amplitude is just a uniform distribution over some specific set of characters, which I'm interested in. What I want to show is that the probability, this will be root h over root g if chi annihilates g, sorry, if chi annihilates h in zero elements. Because if I know the annihilator of h, I can reconstruct h. That's what the original algorithm was about. Now that sounds like a group theoretic property, but there is a diagrammatic way of writing it without, again, relying on group theory whatsoever. And it's the following. Well, if it annihilates h, then I can consider the injection of h into g, or better, its linear extension to group algebras. And I can take one chi, and this will just be the deletion map on h. It will just be 1 over all the basis element. That's what it means to be an annihilator. Because this is if and only if I of h is 1 for every h in the subgroup, and that's just the definition of the annihilator. So that's good. That's a property. What does this map? What do we know about this injection map diagrammatically? Well, we know it satisfies the short exact property with respect to q. This q goes into the quotient. So in fact, we can write this relation as, well, whatever h you add, it goes to 0. So you delete whatever h you add, and you take the group unit of your h. And that defines what this injection is with respect to the quotient map that we had before. In fact, it defines both of them. And with this, it is very straightforward to prove that, I write if and only if, but in fact that will be satisfied, so the consequence will be satisfied. It's straightforward to prove that this is true. So if I take something in the quotient group, and I take something in h, and I multiply them in g, then this is the same as just discarding whatever was in h. Because things, the pre-images of things in the quotient group are invariant under the action of h. This is a key fact from group theory, but it is possible to prove it diagrammatically with 3 steps. And I won't have time right now to do it, but I can do it later on if anybody is interested to see how you just twist two things and it comes out. The interesting observation is that this is equivalent to that, but that is, we know to be true. It's the defining property of the injection, and therefore we can use this. How do we use this to prove what we're interested in? Well, it's actually remarkably straightforward. I want to show that, in particular, this vanishes unless x has that form. So what we can show is that, for example, either x is in the annihilator or this vanishes. And what we can do is the following. We can show that, sorry. The chi acting on this multiplication. Now we know that this is just because chi was a copied element. This is just chi acting on one side, chi acting on the other side. But from our theorem, we also know that this is actually just chi acting on one side and discarding everything on the other side. So either this part is the zero map, or we can cancel it out by applying an orbit state. And these two are actually equal. So either is uniformly zero, or chi is in the annihilator by our graphical definition of it. If this is not zero, then I'm going to take one state where it's not zero. I'm going to precompose by that state. I'm going to get a non-zero complex number. I'm going to cancel that number out. And I'm going to obtain the other. Okay? Now, once I have this, then I can pretty much conclude what I wanted. So that is true. I want to show this. Well, instead of doing what the original algorithm does, which is evaluating the bottom part, so in the original algorithm you took this and you tried to compute what it was as a superposition of group elements, and then you looked at the action of the character on that, you did some sums, you simplified some roots of unity, and you got zero where you wanted it to be zero. In this case, I'm instead going to look at this part. And I'm going to simplify that, because diagrammatically that's easier. And I know yes, sorry, this had a, I forgot to normalize this. Yeah, now I know that either that is zero, and that will be enough if chi does not belong to the annihilator. That would be enough to say that the only things that I'm sampling are things in the annihilator. But that's not sufficient to have a decent algorithm, because you need to be sure that you can sample all of the annihilator somehow. In fact, what turns out, you can sample it uniformly. So I will still have to do something with the other part. Now, in the other case, I will just expand this using that relation that I proved. And I'm going to say that this is actually just chi multiplied by Q dagger applied to that state on one side, and injection applied to the normalized unit on the other side. Now this I can rewrite as the product of yes.
Wait, can't you just use that second equation in either or?
In the?
You wrote either this thing 0 or
yeah, I need yeah, but you need to use it on I. Yeah, so first I have to distribute it over I. Now that I know that I'm in this case, I have to first distribute.
It's on I, not on Q.
Yeah. So this is 1, and this will be the other part. And there are factors. I guess these will simplify to give 1 over root g. I had another factor somewhere. I guess it doesn't matter. I'll simplify to this. All right. So I have this. I have this. Now I know that this one is simply this. And I know that this one will be this state mapped onto some superposition state, but ultimately that will be unbiased. So in particular, I can write this as, sorry, I can write this, and this is also correct. Yeah, that's what I want to write. Yes, apologies. I take this and I expand it like this, because I can just take the pre-image and I can ignore the other h factors by just adding them up on the side. Like this. So I don't have any fluid. That was my point. And now I want to use mutual unbias of these. And mutual unbias of these says that 1 over root g times one of these ones is just 1 over root g. And I want to evaluate this. Now, the norm of this one was h, so this gives you h. And I had 1 over h dangling there from before. There we go, this is included in this calculation. So I get 1 over root h that was out as a scalar. From the unbiased, I get 1 over root, sorry, I had a root g over, no, that was just correct. And I get 1 over root g from the unbiased, and I get h from the fact that this was not normalized. I didn't think it to be normalized. So I get this product, and this is just root h over root size of g, which shows that the probability amplitude, so the square root of the probability of observing something in the annihilator is non-zero, and in fact it's independent of the time in the annihilator, so you are uniformly sampling the annihilator and nothing else. And the sanity check would be to show that, well, this square sums up to 1 in the annihilator, and that's very straightforward because the size of the annihilator is equal to the size of the quotient. So in particular, the sum overall of the elements of the annihilator of h over g is 1, which is a good check. And this concludes it, and I didn't at any point use any group theory. Yeah, that's pretty much it.
While you think about the question, why don't I get our next speaker, Sean, I think, will come.
Yes.
The last sentence of your talk was, and I didn't use any group theory. So, have you really not used group theory, or have you given it in intuitions? And if indeed you haven't used group theory, what does that tell us about the nature of the problem?
Okay. It's not hidden in the sense that, let's see, the previous graphical treatment of this problem did exactly that. It hid the group theory into intuitions about which simplifications had to be made and which maps did. So it was graphical, but then in the end there was maybe 5 pages of group theory theorems and lemmas that said exactly what is what. In this case, there is no group theory, because the group theory is not hidden but stored, if you wish, in strong complementarity. This is equivalent to group theory by a theorem that characterizes exactly which of these things in Hill give strong complementary pairs of observables.
So but the root work, there is a certain amount of work to be done, and it presents itself in the bottom left-hand corner of that board.
Well, actually, proving that this is a group is immediately straightforward. I can do it in 2 lines. Because this is multiplication of 2 elements. And when you put 2 elements here, this will be the statement that multiplication of 2 elements is also copied. So in particular, multiplication is closed as a map. It has a unit, and it has an inverse. So it is a group operation. It is actually, you apply 2 elements in the basis and it follows. Observing that that was the thing to do was, like, it took some good intuition, I guess. But once you see that, the proof is actually not hard. There is no legwork, it's just this formula is stronger in a certain sense.
So there is some post-processing in the sense that what you get out is the annihilator, and then you need to know I can efficiently get the subgroup out of the annihilator, and you do this by taking the annihilator again.
Oh, yes.
Which is some...
And that is where because all of this actually works in the non-abelian case, with a slightly different thing here. Instead of a multiplicative card, you take a card. It also works, and the problem with the non-abelian case is that the post-processing that from the annihilator goes to the hidden subgroup is actually impossible. If the subgroup is not
impossible.
Yes, if the subgroup is not normal, then you can't distinguish between any 2 conjugate subgroups. But if you take the normal subgroup, then the problem is not there. There is some intuition that you can do it. How hard it really is to do is unclear.